Hello everyone. In this video, we are going to see the simulation of circulating current mode operation of 2-volt converter. In the last video, we have seen the non-circulating current mode operation of 2-volt converter. In non-circulating current mode, the two converters, P and the N converters, they'll be operated only one converter at one time. But in circulating current mode, both the converters can be operated at the same time. So when two converters are operated at the same time, we will be having these circulating current flowing in between the two converters. The current may damage the devices. So in order to limit the current, we need to have the reactor between the two converters. So the difference between the two converter is that in non-circulating current mode, only one converter will be operated at one time. But in circulating current mode, both the converters can operate at the same time. To limit the current, we need to have the reactor in between the two converters. So let us draw the circuit. Open MATLAB and open Simulink. Now let us create a block model. Now we have to draw the circuit. So we will have the thyristor, type thyristor in the model, and let us rotate the thyristor. And we will be having 4 thyristors. The thyristor should be connected in bridge fashion. And then we need to have a AC voltage source. Let us change the voltage to 200 volts and the frequency to 50 Hertz. And we need to connect the voltage source to the input of the bridge. Then we will be having the same converter and these two converters should be connected in anti-parallel. And the second converter also should be connected to the same AC voltage source. And in between the two converters, we need to have the reactor. So let us have the RLC series branch and choose only L and let the inductance be 20 millihenry. So this side also we need to have two equal reactors, and we need to connect the load between the midpoint of the two reactors. Let us have the RL load. So again, let us type RLC series branch and let us rotate the branch, and we need to have only RL. Let us take the resistance to be 10 ohms and the inductance to be 20 millihenry. And we need to have the pulse generator. Let the amplitude be 5 and time period is nothing but 1 divided by frequency. and let the pulse width be 5%, and let us choose the phase delay as 60 degree. So we need to have the 60 degree in time equivalent. So 60 divided by 360 into the time period, which is 0.02. And the same pulse generator should be connected to the diagonal elements of the first converter. And we need to have the other pulse generator. The time period of the other two devices should be 180 plus 60 degree. So we need to add the time corresponding to 180 degree, which is 0.01. And similarly, we need to feed the devices of the second converter with a firing angle. So if we choose alpha 1, that is firing angle of first converter as alpha 1, the firing angle of the second converter should be 180 minus alpha 1. So since we have taken 60 degree as the alpha 1, the firing angle for the second converter, that is alpha 2, should be 180 minus 60, which is nothing but 120. So the second converter is fed with a pulse generator of firing angle 120 degree. The first set of switches, that is these two switches, this switch and this switch, should be given 120 degree. The other set of devices should be given 120 plus 180 degrees, so 0 plus 0.01. So these two switches are given with firing angle of 120 degree, and these two switches are given with a firing angle of 120 plus 180 degrees. So we are adding 0.01 corresponding to time of 180 degree. So the other set of devices should be connected to the second pulse generator. Now we need to measure the output voltage of the first converter, the second converter, and the voltage across the reactor. So let us have voltage measurement block to measure the output voltage of the first converter. Then to measure the output voltage of the second converter, again we need to connect the voltage measurement block. Then to measure the output voltage of the to measure the voltage across the reactor, we need to connect another voltage measurement block in parallel with the reactors. Then in order to see the waveform, we need to have scope. So let us have the first input to the scope as the output voltage of the first converter. The second input, let us have it as the output voltage of the second converter. Then we will have the third input to the scope as the voltage of the reactor. So the first waveform will be the output voltage of the first converter. The second waveform will be the output voltage of the second converter, and the third one will be the voltage across the reactor. Now the circuit is ready to run. Before that, we will replace the power GUI. And let us run this model for 0.2 seconds. Now we can see the output waveforms. We see the waveform in the three different planes. So we can see that the first waveform is nothing but the output voltage of the first converter. Since the converter 1 firing angle is chosen as 60 degree, the converter 1 is now operating as the rectifier, and this is the output voltage of the second converter, which is acting as the inverter, because we have taken the firing angle of the converter 2 as 120 degree. And the difference between the reactor voltage is nothing but the difference between the V01 and V02. So the reactor voltage, which is coming like this. So in this video, we have seen the simulation of circulating current mode operation of dual converter. We can change the firing angles, and we can see the waveforms for different values of firing angles. If we choose the firing angle of the converter 1 as greater than 90 degree, then in that case, converter 1 will operate as inverter, and the converter 2 will operate as rectifier, and the difference of V01 and V02 will be the reactor voltage. Thank you.